In this video, we're going to go through section 6.5 of the calculus textbook. We're going to talk about the average value of a function. It is easy to calculate the average value of finitely many numbers. So they have n numbers here. And to calculate the average, as you know, you add up those n numbers and divide by n. But how do we compute the average temperature during a day if infinitely many temperature readings are possible? Figure 1 shows the graph of a temperature function. The temperature is a function of time, where t is measured in hours, and capital T, where lowercase t is measured in hours, and capital T in degrees Celsius, and a guess at the average temperature T average. Yeah, so they're saying during the course of a day here that there's a temperature function, right, that gives the temperature as a function of time, where t is in hours. And what if you want to know what's the average temperature? What was the average temperature during this day? Well, you can't just add up the temperatures and divide by the number of data points, because it's a continuous function. There's infinitely many temperatures. So how do you compute the average temperature in this case? So this is a really interesting application, right? This idea of finding the average value of a function over an interval. In general, let's try to compute the average value of a function, y is equal to f of x, over some interval from x is equal to a to x is equal to b. We start by dividing the interval from a to b into n equal subintervals, each with length delta x is equal to b minus a over n. Then we choose points x1 star to xn star in successive subintervals and calculate the average of the numbers. So we're going to first, to answer this question of finding the average value of a function, we're going to think about dividing the interval from a to b into n equal subintervals of with delta x is equal to b minus a over n. And then we're going to choose points within each subinterval. We can pick whatever point we want. That's these x1 star to xn star to evaluate the function. And then we evaluate we add up all of the function evaluations at each of these x points and divide by n. And what you can think about is that when you take the limit as n approaches infinity, then that's a very good definition for the average. Why is that? Because the idea is you're including in this sum here infinitely many points, because you're taking the limit as n goes to infinity. That's the whole idea. We can't just apply to find the average in general. You just add up all the data points and divide by the number of data points. Well, here we have an infinite number of data points. And so the perfect definition for the average then is, we calculate the average of, and you can look at it like an infinite number of data points, right? We break this up into equal width pieces and then take the limit as the number of those pieces goes to infinity. That's in essence what you're doing. Because when you break this up into like a finite number of intervals, all you're doing there, so like for this formula here, all you're doing is you're just choosing specific points in the interval to use to calculate the average, right? That's all you're doing, right? It's not like we choose points that aren't on the function whenever if we're doing n is equal to 50. No, we're just choosing 50 points on the function when n is equal to 50 to use to calculate the average. Well, based on the definition of average, we would like to choose as many points as possible, more than 50, more than 100, as many points as possible. So that's what we do. When we're taking the limit as n goes to infinity of this, we're saying, in effect, we want to use for the average calculation as many points as possible. Okay, so let's continue to develop this. It says since delta x is equal to b minus a over n, we can write n is equal to b minus a over delta x, and the average value becomes, so they substitute n here, 1 over b minus a, the sum of the function values evaluated within each interval, delta x. The delta x comes from here. Okay, now they bring the delta x into this sum here, and they do that because now you can recognize what this is. This is the sum from I is equal to 1 to n of f of xi star delta x. That's an integral. This is a Riemann sum. But if we take the limit as n goes to infinity, then what happens? 1 over b minus a is not a function of n. So you can bring the 1 over b minus a out front of the limit. and you're left with the limit as n goes to infinity of this Riemann sum. That's an integral. So they turned into an integral from a to b f of x dx. And that's the average value of a function over an interval. 1 over b minus a, the integral from a to b, f of x dx. Okay? And so here they give an example. Find the average value of this function over this interval. We'll work examples. Plenty of example problems. But, you know, I think it's a little clear when they give a real-life application. So you've got this temperature function for over the course of a day, and you want to know what is the average temperature during that day. Now, you know, to get this continuous temperature function, they had to. This function was created from data points, right? There's no experimental data collection that comes out continuous like that. It's always going to be, you know, some individual points. Even if you've got a temperature sensor that records temperatures at 50 readings per second, it's still individual data points. And so in that sense, I mean, I guess technically to get the average, you would like put that into Excel and get the average. But still, though, it's still interesting to think about if you do have a continuous curve, which has an infinite number of points over any interval, what's the average of that function over the interval? So it says if the temperature as a function of time is the temperature at time t, we might wonder if there's a specific time when the temperature is the same as the average temperature. For the temperature function graphed in figure 1, what we just looked at, we see that there are 2 such times, just before noon and just before midnight. Okay, so what they're saying is, here's the average temperature, this pink line, and there's 2 temperatures where the function equals the average temperature. Okay, it says, in general, there is a number c at which the value of a function f is exactly equal to the average value of the function. That is, f of c is equal to f average. The following theorem says that this is true for continuous functions. So the mean value theorem for integrals is just saying that if you have a continuous function over an interval, then that's obviously going to have an average value that we just talked about how to calculate. But the theorem is that if the function is continuous, there will be an average value, but then the function will 100% be equal to that average value at least at one point. That's the mean value theorem for integrals. And there was a mean value theorem that we talked about earlier in relation to derivatives, and we'll go back to that in a second. But so it's just saying if f is continuous on the interval a to b, then there exists a number c, at least one number c in a to b, such that if you evaluate the function at c, then it's equal to the average. And so here's the average, and then what they do here is they multiply both sides by b minus a, so you have f of c times b minus a is equal to this integral, and they do that for a reason. It's another way you can look at the mean value theorem for integrals. We'll talk about that in a second. We can talk about it right now. What this is illustrating is that one way you can think about the mean value theorem geometrically is, so if you're dealing with an interval over a function where the function is always positive, so this function is always positive, then the idea is that at the f of c, at when you evaluate the function at f of c, right? So this is equal to the height of the function is equal to the average value. Then the area of this rectangle here, so b minus a times f of c, that's what this is, right? F of c times b minus a is equal to the area under the curve. And you see, that's what this is. So that's one way of thinking about it. But, you know, if you had this theorem applies universally. So even if you had a function that, you know, did like that, and you were calculating you're doing the mean value theorem over like this interval, well, then, you know, the definite integral is like the net area, right? And so, again, the theorem still works, but it's hard to get a sense for the meaning of it, the meaning of this when you're using like a net area, as opposed to this gives you a better geometrical sense of it. Okay, but it says the mean value theorem for integrals is a consequence of the mean value theorem for derivatives in the fundamental theorem of calculus. So, you know, we're not going to get into the details of the proof, but let's go back to the mean value theorem for derivatives, just to compare these two. So this was in chapter 4, on applications of differentiation. So, I mean, look, we can look at Rolle's theorem too. Why not? They were all in the same section. So, Rolle's theorem said if there's a function that satisfies these three hypotheses, so f is continuous in the closed interval a to b, f is differentiable on the open interval from a to b, f evaluated at a is equal to f evaluated at b, then there's a number c in the interval a to b such that f prime c is equal to 0. That was Rolle's theorem. So f of a is equal to f of b, so that the function evaluated at a is equal to the function evaluated at b. The function is continuous on the interval, in the closed interval it says, and differentiable, so it doesn't, so the function evaluated at a is equal to the function evaluated at b. Here, the function is continuous, but it's not differentiable, so this isn't included. But if it's differentiable, it's continuous, and it's f of a is equal to f of b, then there must be a number c within a and b such that the first derivative is equal to 0, at least 1. That was Rolle's theorem, okay? And then it says here that our main use of Rolle's theorem is in proving the following important theorem, which was first stated by another French mathematician, Joseph Louis Lagrange. So Rolle's theorem was used to prove the mean value theorem in relation to differentiation, which says that let f be a function that satisfies the following hypotheses. So once again, f is continuous in the closed interval from a to b. F is also differentiable. But here, it doesn't say that f of a has to be equal to f of b. Then there is a number c in a to b such that f prime of c is equal to f of b minus f of a over b minus a. And what this meant was that, so this here was the secant line, or the slope of the line between the two endpoints. So if we come here, you see, that's the slope of this line. F evaluated at b minus f evaluated at a over b minus a, that's the slope of this line. That's the slope of this line. And so what the mean value theorem is saying is that, for differentiation, what it's saying is that under these conditions, whether the function is continuous and is differentiable, that there's going to be at least one point then, in that case, there's going to be at least one point x within a and b, where the derivative of the function evaluated at that point is equal to that slope of the secant line, right? So the idea is the way they try to describe this is like if you have this slope of the secant line, or the slope of the endpoint, the slope of the line between the two endpoints. And if you take a line that's parallel to that line and it's off in space, and you start bringing it in towards the function, it's going to be tangent to the function at least 1 point. And so in this case, it's 2 points. That's the idea of the mean value theorem in relation to differentiation. Okay? And then, once again, the mean value theorem in relation to integration is saying that if you have a continuous function on a to b, so it doesn't say anything about being differentiable, just if the function is continuous on the closed interval from a to b, then there's going to be at least one number, c, in a to b, such that the value of the function evaluated at that point is equal to the average value of the function over the interval, which you can interpret this geometrically. If you have a function that's positive for all a to b, then the area under the curve from a to b is equal to the area under a rectangle that's equal to the function evaluated at some point c times the interval b minus a. So like you could think about, let's say you didn't know the f of c, like the point c where you plug it into the function, then the value of the function equals the average value of the function over the interval. What you could do is you could calculate the area under the curve between a and b. Then you could find a rectangle whose width is b minus a, and height c you don't know, but the height c you find by you play with the c value until you get the area that's equal to the area under the actual curve, and you know that that's equal to the average value of the function. And you know that that point c then is equal to, when you evaluate f of c, that's the average value of the function. So, but again, this geometric interpretation is just for a special case where the function is always positive, but still useful to think about, to understand that this mean value theorem for integrals. So it says the geometric interpretation of the mean value theorem for integrals is that for positive functions, there's a number c such that the rectangle with base a to b and height f of c has the same area as the region under the graph of f from a to b. Yeah. All right, so then they give some more examples. We're going to work a bunch of examples. And that's it for this section. So that's the average value of a function over an interval. Now let's work some example problems.